Hello, I'm excited to embark on this journey of discovery with you. We're about to unravel the mysteries behind one of the most impactful inventions of the 20th century. Ever watched a massive Airbus A380 liftoff, seemingly defying gravity with effortless grace? And wondered how something so heavy, packed with hundreds of people and tons of luggage, can fly? It's a question that sparks curiosity in all of us. It's not magic. It's engineering, a testament to human ingenuity and our relentless pursuit of innovation. The key to this aerial feat, the jet engine, a marvel of engineering that has revolutionized air travel. Jet engines gulp air in massive quantities, like a hungry giant taking a deep breath. Then they ignite fuel, creating a controlled explosion of immense power, and blast it out the back, generating a powerful thrust that propels the aircraft forward, propelling planes forward faster and farther than ever before imagined. This invention shrank our world, connecting distant lands and cultures in unprecedented ways, making overnight trips across continents routine, a concept that would have seemed like science fiction just a century ago. Without jet engines, travel would be slow, a far cry from the speed and efficiency we enjoy today. Business limited, hindering global commerce and collaboration, and global connections rare, isolating communities and limiting our understanding of the world. Understanding how they work isn't just for engineers. It's for anyone curious about the world around them. It's about grasping a key part of modern life and appreciating the technology that shapes our experiences. At first glance, a jet engine looks complex, a bewildering array of parts working in perfect harmony. A long pod packed with spinning blades and pipes, a mechanical symphony of precision and power. But the core idea is simple physics, principles that you might even remember from high school, and we'll break it down step by step, making it easy to understand and appreciate. We'll follow a single particle of air, tracing its journey through the engine, as it's sucked in at incredible speed, pulled into the heart of the machine, squeezed, compressed to increase its energy and potential, ignited, mixed with fuel to create a powerful, expanding force, and fired out the back, creating the thrust that powers the plane. And by the end, you'll know exactly how that roaring machine, that symbol of modern aviation, gets us off the ground, soaring through the skies with speed and efficiency. Let's dive in and unlock the secrets of the jet engine. Before we get inside the engine and explore its intricate workings, let's take a moment to talk physics. Understanding the fundamental principles at play is crucial to appreciating the ingenuity of jet engine design. Specifically, we need to revisit one of the cornerstones of classical mechanics, Newton's third law of motion. This law, formulated by Sir Isaac Newton centuries ago, is surprisingly simple yet profoundly impactful. It states that for every action, there's an equal and opposite reaction. This isn't just some abstract concept confined to textbooks. It's a fundamental truth that governs much of the physical world around us. A perfect everyday illustration of this law in action is what happens when you release an inflated balloon. As the air rushes out one way, propelled by the internal pressure, the balloon shoots the other way, seemingly at random. The escaping air exerts a force, and the balloon responds with an equal and opposite force, resulting in its erratic flight. Now, a jet engine might seem a world away from a simple balloon, but at its heart, it's simply a controlled, powerful, and highly refined version of that balloon principle. It's harnessing Newton's third law to generate immense thrust. It sucks in a massive amount of air, then accelerates it to incredible speeds and blasts it out the back with tremendous force. The backward rush of this incredibly hot, high-velocity air is the action, the force being exerted, and, as Newton's law dictates, the forward movement of the plane, hurtling down the runway or soaring through the sky, is the equal and opposite reaction. This propulsive force, this reaction to the expelled air, is what we call thrust. It's the driving force behind jet aviation. The more air you move through the engine and the faster you accelerate it before expelling it, the more thrust you generate. It's a direct relationship. It's important to understand that the engine isn't pushing against the air behind it, like a boat propeller pushing against the water. Instead, it's pushing itself forward by forcefully expelling gas rearward. This principle is so fundamental that it works even in the vacuum of space. It's the very mechanism by which rockets fly, unhindered by the absence of an atmosphere. The real challenge for engineers throughout the history of aviation was building a machine, a jet engine that could perform this process efficiently and reliably day in and day out, lifting hundreds of tons of aircraft and passengers safely into the sky. The ingenious solution they devised is a thermodynamic cycle that can be summed up in just 4 simple words: suck, squeeze, bang, blow. So let's start our journey through the engine right at the front, the suck stage. This is where the magic of jet propulsion truly begins, where the atmosphere is drawn in to feed the engine's insatiable appetite. Ready to dive in and see how it all works? Our journey starts at the front, the fan. This giant spinning fan sucks in a massive amount of air, enough to fill an Olympic pool every few seconds. That's the suck. Behind the fan is the compressor, a series of spinning blades and stationary blades that squeeze the air tighter and tighter, raising its pressure up to 40 times normal. Compressed air is packed with energy like a coiled spring. The more you squeeze, the bigger the bang when fuel is added. Only a portion of the air goes into the core for compression, the rest bypasses it. More on that later. The result, a torrent of hot, dense, high-pressure air primed for combustion. We've sucked and squeezed, now it's time for the bang. Let's see what happens next. Onward. The compressed air enters the combustor, the engine's fiery heart. Here, fuel is sprayed in and ignited, mixing with the air in a controlled, continuous burn. Temperatures soar above 2,000 degrees Celsius, hot enough to melt metal. To prevent disaster, only part of the air is burned. The rest cools the chamber walls. The result? A huge volume of hot, high-pressure gas, desperate to escape. This is where chemical energy from fuel becomes thermal and kinetic energy. The expanding gas rushes out, but before it leaves, it has one more job: powering the engine itself. The cycle isn't just about thrust, it's about keeping the whole system running. Next, the turbine. Let's see how it all stays in motion. The blazing gas slams into the turbine, a set of bladed discs like windmills that spin at incredible speeds. The turbine extracts energy from the gas, converting it into mechanical power. This power spins a shaft running through the engine, driving both the compressor and the fan at the front. It's a self-sustaining loop. The bang powers the suck and squeeze. Turbine blades endure extreme heat and force made from superalloys and cooled by clever engineering. Up to 75% of the energy from combustion is used to keep the engine running. Even after all that, the gas is still hot and fast, ready for the final push. The last stage, the nozzle. Let's finish the journey. Here comes the blow. The hot gas exits the turbine and enters the nozzle, the engine's exhaust. The nozzle's shape accelerates the gas even more, blasting it out at supersonic speeds. This high-speed jet of gas is the action that creates the reaction, thrust. The faster and more massive the expelled gas, the greater the thrust. The difference between the air's entry and exit speed is what propels the plane. Every part of the engine works in perfect sequence, turning fuel into forward motion in a split second. It's a continuous balanced flow. Suck, squeeze, bang, blow. That's how a jet engine works, from intake to exhaust. But there's one more twist. The bypass engine. Let's explain. Modern airliners use high bypass turbofans, not simple turbojets. Only about 10% of the air sucked in goes through the core. The other 90% bypasses it, flowing around the engine. The big fan at the front acts like a ducted propeller, accelerating this bypass air. Thrust comes from both the hot core exhaust and the cooler, fast-moving bypass air. This design is quieter and far more fuel efficient. The bypass air muffles noise and improves efficiency, making long-haul travel practical and affordable. That's why modern engines look so big. The core is small, the fan and bypass duct are huge. Next time you fly, look at the engine. You're seeing a high bypass turbofan in action. It's a clever hybrid, giving us the best of both worlds. Efficient, powerful and quiet. That's progress. A few quick facts to blow your mind. The tips of fan blades can travel faster than the speed of sound, creating that signature buzzsaw noise. Each blade is a marvel, hollow titanium, strong and light and more expensive than a car. Inside, pressures reach 40 times atmospheric and temperatures exceed volcanic lava. Turbine blades withstand forces equal to hanging a bus from their tips. Engines are tested with frozen chickens and ice blocks to ensure safety after bird strikes or hail. A single GE90 engine on a Boeing 777 produces more power than all the Titanic's steam pistons combined, and there are two on each plane. All this from a principle you can demonstrate with a party balloon. Scaled up, of course. The jet engine, a marvel of engineering, fundamentally transformed our world, shrinking distances and connecting cultures in ways previously unimaginable. It revolutionized travel and commerce. It turned distant continents into overnight destinations, making the world feel smaller and more accessible than ever before. This innovation made global travel fast and accessible to a wider range of people, not just the elite. Before jets, travel was slow, expensive, and rare, often taking days or even weeks to reach far-off places. Now, families can easily plan vacations to exotic locations, creating memories that last a lifetime. Students can pursue educational opportunities abroad, broadening their horizons and fostering international understanding, and businesses connect across the globe with ease, expanding their markets and fostering international collaborations. The jet engine fueled economic growth by facilitating the rapid transport of goods and services across borders. It also fostered cultural exchange, allowing people from different backgrounds to interact and learn from one another. And it spurred the rise of global tourism, enabling millions to explore new places and experience different cultures. It physically connected the world, creating a network of routes that span the globe. It did so long before the internet did so digitally, paving the way for the interconnected world we know today. Of course, jet engines burn a lot of fuel, a necessary trade-off for the speed and convenience they provide, and they contribute to emissions, posing a significant environmental challenge that we must address. But engineers are tackling this challenge head-on, developing new technologies to reduce emissions and improve fuel efficiency. And despite these challenges, their legacy is secure. They shrank the world and reshaped society, leaving an indelible mark on human history. So next time you hear a plane overhead, remember, that's the sound of our interconnected world, a testament to human ingenuity and our desire to explore and connect. It's the roar of progress, a symbol of our relentless pursuit of innovation and advancement. And that, when you think about it, is rather brilliant, a remarkable achievement that has transformed our lives in countless ways. Thanks for watching. See you in the skies.